Let's zoom. Can you hear me?
Yeah, you're good.
Thanks. Okay. Hopefully the computer will get itself work. Otherwise, we'll have to censorize the OBS a bit. It's a huge. Okay, people survived after the analysis from last time, the randomized analysis, expectation, etc. How we did it. With a quick sort, there was one ugly double summation with two indices, but once you looked at it again, you saw that the element 1 over k, for every value of k, 1 over k appears exactly n times, and that was the whole deal with the two indices. Appears at most 1 over n times, or n minus 1, or n minus 2, or n minus 3, and once you summed it up, it all somehow survived. But yeah, if you thought that it was terribly good or terribly bad, this randomized analysis, please let me know. And meantime, I want to chat, to prepare you about to something that I'm going to ask in the homework. It goes like this. It's one of the questions, not the easiest, not the hardest. Computer relaxed a bit. Here I have a little program that finds the maximum out of n random elements. So what's going on here? I set the counter to be 0, I set m to be minus infinity, and now I repeat n times, add even parentheses, that for I goes from 1 to n, that is I repeat n times, I pick a random number between 0 and 1, real of course, no, it doesn't have to be 0, 1, it could be 0.3, and if x is larger than the maximum that I had so far, maximum that I've seen so far, I set the new maximum to be x, and I increment the counter. Because I increment the counter every time that I saw a number that is larger than everything I've seen so far. Both waiting, we update the counter, update update m every time we see a number largest than all previous. Every time that I see a number that is larger than all the previous numbers, I update m to be the new number. You know, it's a very stupid way to find the maximum, but whatever. And I increment the counter. Okay. And as a warm-up, let's ask what is the max value of the counter? Again, the counter asks how many times do they have to update the maximum. What? Exactly n. If every random number that I pick is larger than the previous one, then of course I'll update it n times. That's the maximum. What's the minimum? That will be if the sequence that I see is monotonically increasing. Not very likely if I pick random numbers. I'll pick first the smallest and the second smallest and the third smallest, but things happen. There is a probability of 1 over n factorial chance that you are landing on a really lucky day, and that will be the numbers that you see. Right? The probability is slim, but it could be. What would be the minimum number of times that I'm updating it? But the minimum, do I update it? It's 1 or 0. Well, I start from minus infinity, so at least once I update. So the minimum number is 1. So the answer was here was n, and the minimum is 1 if, of course, my sequence is, for example, decreasing. That's actually a bit more likely because if the largest number that I picked largest than any other number, then I don't update m at all. And my question would be, of course, to ask how many times on average are we updating it. And surprisingly, it will be the base of a linear programming algorithm. What you see over there will help us to solve the linear programming algorithm, and which in a sense is like finding the maximum, but in 2 or 3 or 4 or more dimensions. So we will see how later in the course how it leads to a really cool algorithm, but in the meantime, at homework 1, I'll ask you to play with this. And especially, I will ask what is the probability that we update m at the ith peak, at the ith iteration. Ith peak, when I equal I, what is the probability is that the second number that I pick, for example, that when I pick my second number, I equal 2, I'll update the counter. I'll update n. Let's play with this a bit. Let's take m equal 2. What's the probability that in my second attempt, when I equal 1, definitely I'm updating the counter. Yeah, I'm updating n, the maximum. No doubt. Right? Because I start when it's in minus infinity, my first iteration, I pick x between 0 and 1, definitely n is larger than 1. Definitely the first number that I'll pick, let's call these numbers, let's add an index here. Definitely my first number, x1, when I pick x1, I'm changing n. Let's move to the case of I equal 2. Probability will be half. And the easy way to think about it is to say I picked x1 and I picked x2. Let's think about them. One of them is larger than the other. But there is no, let's think about these two numbers that I just picked. There is no reason to think that they picked in an order at which the first is larger than the second or the first is smaller. It's complete symmetry. So the probability when I pick 2 is half. What about the case of 3? I equals 3. Sorry? The probability will be 1 over 3, and that's correct. And how do you know? Sorry? Let's say that it's real numbers, so the probability is that it's exactly the same. Don't worry about it.
It's the same idea, right? The order doesn't matter.
We picked 3 numbers. We can decide about this process as first pick 3 numbers, which values you are picking, and then pick the order at which you are arranged. One of the 3 numbers, x1, x2, x3, one of these 3 numbers is the largest one. What the probability is that it appears at x3 maybe is the largest one. What is the probability that x3 will appear as a last element? That is, that's at the third iteration. I'm updating m. It's exactly the same probability that x3 will be the second number that I pick. It's exactly the same probability that x3 is actually the first number that I pick. It's complete symmetry. Out of all the ith number that you pick in the ith iteration, the probability that the largest one was the very last one is exactly the same probability that it is one before, exactly the same probability that the largest one was appeared 2 steps before, and so on. So for general I, it will be easy? 1 over I for general I, for every I. Somebody sees already, but what will be, how many times will you update m on average? That's slightly more complicated. That would be the homework, actually. Yeah. So I'll ask you in the homework to use random variables, Boolean random variables. For convenient, they might be 0 or 1, depending on something happens. Then the number of times that m is updated is the sum of these Boolean values every time that you're updating n. One of these random variables is 1. Again, think about random variables as a flag. Something happened, something did not happen. Updating m or not. And you will look for the expected value of the sum, which is in turn the sum of the expected value of each one of them, which is in turn just the sum of their probabilities. Okay, if everybody's convenient, let's talk about amortized analysis. Where amortized analysis sometimes get questions. Amortized analysis, it's not the whole of homework, but that would be this question exactly, and you'll be surprised of how useful this little trick is, just to think about the symmetry and that there is nothing particularly likely that happens only at the I step. Amortized analysis. I started to talk about it in the end of the last meeting, but that was very briefly. It's a method to account for algorithms where you have algorithm, which it's not probabilistic analysis. It is talking about the worst case time, but we're using amortized analysis to say we are performing a sequence of operations on some data structure, and one particular operation might be quite costly, and we are performing a sequence of operations. So a naive cursory analysis is could be the maximum time per operation times the number of operations. Could be quite large, but if we use a more settled argument, we will see that a sequence of operation is not too bad. Okay, so the three methods of amortized analysis, you'll find it either a aggregated analysis, should say, I want to ask what is the average work per operation, but it's average not in the sense of probabilistic analysis, what the expected one, but it's a hardcore average. Take the sequence of take the overall work that you spend for a sequence of m operations and divide it by the number of operations, how much each operation takes. That would be the aggregated analysis. The accounting method that we kind of already saw it in context of a quick sort. Accounting method said that assign for each type of operation some cost, some credit that I'm getting to every item in my data structure. In the quick sort, we put log n dollar on every key, and then every time that this key was merged in an array with another key or was moved from one place to another, we charge this key $1. We'll see other useful usage of the same trick. Assign some cost, some charge for each operation, put some amount of dollars, some credits, and if there is some credit left, maybe you'll have to shift credit from one key to another key. We didn't have it in the quick sort, but we'll see it soon. We might need to shift keys, but the idea would be we always in the green. We always we never overdraft. We never takes too many dollars. For every time that we are performing an operation, there is somebody to pay for this operation. Every time that our computer spends a constant time, one of the elements in our data structure is capable of paying for it. Sounds very confusing. A quick example is coming up. Very easy. Another method is a potential method that talks about something like energy function of the whole structure that I will not use today. Not use in this course. Assign like an energy function that can show that you're never running out of energies. Okay. Stack. You all know stacks. Here is a stack S, and I can do push of an element into X, say push 3 and then push 5. So into the stack 3 is the first element that is inserted. Then I'll do push 17. So I'm inserting 3. Then the next push will insert 5. Then I'll insert 17. And now in a stack, you also have the operation of top that tells you what is at the top of the stack. If it's a really formal stack, then that's the only element that you can see. And if you perform pop, then the element which is at the top of the stack will vanish, will go out, right? And that's the only order. And so the next pop will take out the 5, and the next pop will take out the 3, and then we are done. Next pop should give an error message. So I'm inserting an element, and from time to time I'm popping 1 or 2 or k elements. Right. So I'm doing some sequence of n push, pop, in any order that you want. Push, push, pop, k times pop, whatever. Any order that you want. And it's really toy example, obviously. What's the worst time per operation that can happen if one of my operation is k pop or multi-pop? Multi-pop can perform k pop operation one after the other. It's a single operation. What's the worst case running time? For a pop operation, for a multi-pop operation, it will be n, obviously. But it could be that I'll put the parameter here as n, and then I'm cleaning the stack completely for n keys that are there. So worst case running time is order n. So, and I'm performing a sequence of n operation, so naive bound on the running time is n times n. What's the actual running time? No matter how I did this, no matter at which order, what's the running time? Just PL it out, it's obvious. N. It's n because what's the rule? In A, notice that I don't have multi-push here. In each operation, I'm inserting one element. Each push, I'm inserting one element. Once an element is popped, it cannot be back into the stack. Okay, so let's understand why it is. So each object can be popped only once, obviously, even if including in the multi-pop, obviously. So a pop is at most. We cannot have more pops operation than the number of pops. Okay. So the average time per operation, and that's, the amortized time per operation will be order n. That's exactly the case that we'll say the amortized time, which is like the time for n operations, the total time for on operations divided by n. It's like the average, except that the average has a connotation of some random thing that happens here. There is nothing random. In other words, it's just the average out of n operations is a constant time, even though the actual work per operation can be n. So the amortized cost is a way to aggregate the analysis that is defined on the average cost. Okay, here is an example that I started to mention in the previous meeting. Binary counter. I have a binary counter, and I perform a sequence of increments on it. Wants to call it, to make it, to start from a. Let's start from zero. Let's do increment over here again, pretending that we are not doing it in hardware. So I'm doing +1 on this boundary counter. What should I do? As long as the binary counter at index k, as long as the boundary counter at index I shows 1, I'm just explaining you how to do long summation from high school. +1, this one will become 0. This one will become 0. This one will become 0. And finally, the last one will become 1. Makes sense. Okay, and the last bit is flipped, obviously. And again, let's assume n operations and increment So I start when all the bits are 0, and I'm performing an incremental algorithm, an incremental operations, sorry. Performing it n times. The number of indices in this array could be k. So naive algorithm could be, say, naive analysis will say what's the maximum time per one increment. You're incrementing all the bits, ignoring overflow. So one operation, one inc operation takes omega of k, theta of k time. That's a worst case. K bits, it takes no more than k, no less than k, in the worst case, when the counter is completely full. And we want to show that it's not the case. Somebody sees? So the worst case takes theta of k. Not that's the case. That's true. But a sequence of n inc operations takes order of nk, which is obviously true. Worst case is k, that's the number of bits. If it confuses you, replace k with log n or replace k with 64 bits, whichever you want to store. But k is not a constant for this analysis. So k bits in the counter. I'm doing an operation. So a bound on the overall running time is order of n times k. That's a correct statement. It is also omega of n times k. That is a tight bound.
No, because if you increment once,
Mm-hmm.
then in the worst case, everything except the zeros, set the loss bits for next time you increment, will only be getting one operation is O1.
My next operation after this very costly, relatively very costly operation is much cheaper. Now when everything is 0, my next increment just costs 1. And somehow rarely I'll have to change 2 bits. More rarely I'll have to change 3 bits. More rarely I'll have to change 4 bits, and so on. Anybody sees a foolproof at this point? Why it's only linear? Remember, order is an upper bound. Sometimes the order is kind of the jokes of, where are we? We are in a balloon. The people that were in a balloon and lost in the storm. It's a correct but useless answer. So it is correct that this is a bound, but it doesn't give us tight enough bound. So, cursory naive analysis, single increment takes order k, sequence of n operation takes order of n times k. Let's show that it's only linear. Again, it's a toy problem. So here is an analysis that I have. Here is one analysis. How frequently do I change the rightmost, the least significant bit? All the time. If I do n increments at each one of the operation, I'm changing the rightmost bit. So the rightmost bit is changed n times. A0 is changed n times. In the sequence of n operations, how many times did I change the second bit, bit 1? If I start counting from 0. How many times did I change this bit? And half. Next bit, n over 4, only over fourth operation, n over 8, n over 16, n over 32 operation. So it's our beloved sum. We've seen it many times in this course, and we will see it several more times. The total work that you're investing is this, which is n times 1 plus half plus 1 over 4 plus dot, 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 dot. And this will end up actually in 1 over k. But we discussed many times, if I'll stop, then the last element is 1 over 2 to the k. That's the exact work that I'm doing. But since I'm lazy, told it many times, I'll say that this summation, that is the exact number, is smaller or equal than n times, it's actually strictly smaller than n times 1 plus half plus 1 over 4 plus, and then I'll add more elements all the way to infinity, just to make this sum nicer. So, and now this number is exactly 2. Okay, so we saw that it's linear work in one way. Here's another way to show that it takes linear time. That is, yeah, I didn't say. Since it takes linear time for an operation, the amortized time, amortized work is order of n, 2 times n divided by n, which says it's order 1 per 1 operation. That would be the amortized work. Sequence of operation, how much did you work for the whole sequence, starting from and divided by the number of operations. So amortized time is 1. Let's use the counting method. It's cool. So we are going to give some credit to each operation, and we are going to charge elements. What are the elements here? The bits of the array. Every time that I'll have a 1, I'll make sure that it's that it have enough credit to pay for whatever happens to this one. So essentially, assign different charges to different operations. Here it will be a toy example. It will start being interesting when I'll talk about dynamic arrays, and it will be more interesting, I probably won't finish it today, when I'll talk about splay trees that are extremely cool. But, and then we will use all these tools. So the amortized cost, or more or less the actual cost, and when the amortized cost is larger than the actual cost, the difference saves to some specific credits of dollar. Yeah, there is a problem with trying to set the rules before we saw more examples of what's happening in practice. We'll get back to this slide later when after we see the examples, and then it will be less abstract. Let $1 represent each unit of cost. Every time that I'm changing a bit, I'm charging this bit. It will cost my computer to change a bit $1. Again, every change of a bit cost me $1. Now, who puts the dollars on it? Every time that what is the source of the money in this track? The user that decides to perform inc, the increment operation, is charged to dollars per every increment operation. So I'm going to charge it to the number of inc operation. So what the rules? Whenever a bit is set, we are paying $1 of the actual cost and store another dollar for this bit as credit. You see this sequence of bits. Each one of them, the old sequence, this old sequence with a 0 at the end, each one of them now have a credit of $1. That will be my invariant. For me as a user, it will cost $2 to perform an increment. And the way that I store the credit, the money in the system, is that each one of the ones will be left with $1. So how does it work? When a bit is set, I'm going to store $1 for it, and $1 is used way for me to the $2 that it cost me to perform the inc. How do I use it? One of these $2 I'm putting on the one that I'm adding right here. So this one, for momentarily, will have actually $2, which we'll see how we are using it. What am I doing with this $1 on each bit? This $1 paying for the cost of making this bit from 1 to 0. Taking a bit and set it from 1 to 0, cost $1. And who pays for it? The bit that we just changed from 1 to 0. That this bit responsibility to pay for it. This bit responsibility. What am I trying to convince you? That if I'll spend $2 per each operation, I'll always have some source of money for each bit to set it from 1 to 0. And you can imagine why it cost me $2. Right? All these bits now are paying for themselves to become 0. I'm doing the increment that I just added 1, doing the increment, the plus 1. This bit will say I'm set to 0, cost me $1. I use this dollar, I use this dollar, I use this dollar, I use this dollar. Remember, this one had $2. One is going to be paid, so this one over here will be used to pay, to store one credit on itself. So this one is left with $1. This one stores $1. What did I do with the other dollar? This one, when it came, had $2 on it. What did I do with the other dollars? I paid for changing this bit from 0 to 1. So what's the invariant here? Every one stores $1 on it. Every time that I perform an operation, I spend, the user that decides about the increment, it costs $2, and nobody runs out of money. No matter how the ones are distributed in the system, no one is have $0. Everyone that is changed can pay for itself. So it's a different way to get to the linear time algorithm numerator, and that has nothing to do with the fact that how frequent or infrequent I'm performing the operations. Right, the analysis before that said to change the ith bit, it happens only in a frequency of n over to the I. To change a kth bit happens extremely rarely. That has nothing to do with it. It just says a bit never runs out of money to pay for it to become 0 or 1. And of course, I need to invest more money every time that I'm performing increment. And you can see that if I would do decrement, then the opposite will not be true. What? One decrement, if I'll have now a sequence of zeros, they don't have any money. I'm doing one decrement. Now all these zeros should be flipped to 1, and there is nobody to pay for it. Okay. Here is a cuter, I think, less artificial problem. So let's talk about the dynamic tables. I'm allocating, it usually comes up in the context of hash tables that we'll discuss in this course. Some amount, and if I have only one table in my whole algorithm, and memory is not an issue because I have multiple thread or whatever, then ignore everything that I said about dynamic arrays. Allocate the maximum size of arrays that you need, that you imagine needing, and you have all the memory in the world because it's only a single table that you are storing. What happens if I have a few tables? Table 1 and table 2 and table 3 and so on, all the way up to table K. Each one stores different items. Items are going to appear or change as the algorithm runs. And this table, I have no clue how many elements do I need to store in it. Same goes for this, same goes for this. Right? So I don't know really how much memory do I need for the whole operation. So I'll take the memories that I do have and I'll start with some reasonable arrays, but one might grow and one might shrink. So at the moment, let's just worry about the goal. So the idea of dynamic tables is that I will start with one table of certain size. For theory, it doesn't matter that I'll start when the size of table 1 is actually 1. There is slides coming, you don't need to write anything. We'll start with a table of slides 1. And when an element is inserted, and I want to add another element, what will I do? I'll copy this element, I'll allocate a new array, ignore the time for cleaning the array from garbage. You do have to worry about it in practice, but unless the operating system takes care of it, I think that Java, ANSI Java, does take care of it, that your array all contains 0. If not, then you have to do it. It doesn't matter. Take this element that filled this table and copy it over here. And when this table is full, then allocate a new table now with size 4. Copy these two elements, which you do have to pay no matter what. Copy these two elements, X and Y, into the new table no matter what. And when W and Z appears and you want to enter a new table, allocate another one. And if I'm short in memory, then if a table becomes contains very few elements, I will measure it as a load factor. How many elements versus how many cells in the table, how many keys versus how many cells. Maybe I want to contract the table once in a while. But either expand or contract are expensive operations. So if I have a lot of elements and a lot of keys and I'm going to copy them, obviously it will take lots of time. So, for the moment, consider only expansion. And when the table becomes full, double its size and reinsert all the elements before that. In hashing terms, you're doing rehash into the new table because you need a new hash function that now addresses the new table. Okay, if I'm just inserting the elements, in this discussion I'll just insert the elements sequentially from the left to the right, it's not. But the same idea will work with hashing. In hashing, we will usually like to keep the table no more than 50% full. Here I'll just assume when it's full, I'll go until it is completely full. Okay, and each time we actually insert an item into the table, we think about it as elementary insertion. So let's think about how much time does a sequence of insertion takes. What is the rule? Each time that my table is full, I'll allocate a new table, which is twice its size. At the homework, I'll ask you to play with different constants. Here, I'll just take a table which is half its size. Inserted 17, the table is full. So the next insertion of 17 and 30, I'll copy the 17 to a new array which is twice its size. Then I copied the elements into an array that is 4 times its size to make room to 17, 30, 22, and 29, and then double the element into an array of size 8, 16, and so on. And the question is, how much work do I spend for all the copying of an element from one array to another? How much work do I, sorry? Exactly. So an element might be copied from an array to the next one. One copying operation takes n time. Right? If I have n elements, it will take linear time to copy it. And how many operations of expand did I take? Before I'm going further with it, what will be the strategy if when I'm allocating an array, I will move from an array of size n to an array of size n plus 1? Let's look for a second at this horrendous strategy. So instead of allocating a new array of size 2n, I'll allocate a new array of size n plus 1. And when this is full, I'll allocate a new array of size n plus 2. If this is my strategy, how much time would it take to insert n keys? N squared. Because it is 1 for copying the first element, plus 2 when I move from 2 to 3, plus 3, plus 4, plus total dot n, which is theta of n squared. That's really good. Better when I double them, then how many times do I copy the 17 from one place to another? The 17 is copied log n, because 2, 4, 8, 1 to 4, 1 to 4, 8, 2 to the i. If I have n keys, then it takes 2 to the i for the last one. So a slightly better bound is n log n, is the overall work that I spend, or log n amortized time. Again, sequence of n operation divided by the number of operations. N insertion will take overall time, n log n, based on this analysis, divided by the number of operations n, giving me n log n. It's still not a tight bound. instead, let's say, CI would be the actual cost of the ith operation. What is CI? If the array is not full, then CI is 1. If the array is full, then I have I minus 1 items in the table to start this operation, having to copy them in times I minus 1, existing items too, and then inserting them, giving me this type of CI is a I plus 1. Okay. Here is a cuter trick.
I have a question. Would it be I instead of I plus 1? Because you're inserting I minus 1 items and then 1 extra item?
Stand corrected. Okay. So CI. So very naive analysis is n operation times order times n time, giving me order of n squared. Better analysis would be n log n. Most students will get to the n log n, obviously, because there are n steps of the expansion. More subtle analysis, amortized analysis will say, let's look at the time in reverse, going back in history. The last operation took n time. That's n times 1, which means that the previous operation, the previous expand operation, took half its time. If now my last array is of size n, one operation ago, my array was of size n half. But 2 operations ago, my array was of size n times quarter. 3 operations, it was 1/8, our beloved sum. All makes it 2n. That's a more subtle analysis. How does it work with a counting system? I'm charging $3 for every insert operations. It will all become more tricky when we'll talk about deletion, at which deletion also pays for something, but not to the somebody that is deleted. It will be transfer of credit. But at the moment, I'm just talking about insertion. Why does it cost me $3? $1 pays for inserting X only. I'll assume that one basic operation takes 1 time, no matter what, every element, no matter if I did expansion or not. $1 pays for X move to another array in the future. This $1 pays for X moving, copying from an array in the future. But notice that to copy this 17, when the 17 sits here, it has some credit, which would be $2 to start it, which will be, it will be left possibly with $1, at most 2. But notice that the 17 is being copied log n times. So this $1 or $2 that it has now, it completely used it when it's the first time that it's being copied, and then it is broke. It's not in overdraft, but the 17 will be broke. So who is going for paying for the next times that 17 is copied? 17 will be copied a few times in the future. Who's going to pay for it? The newer elements that will come after the 17. The newer elements that will come after the 17 will pay for the 17. $1 pays for some other items to be moved. The rule would be that the newest key transfer credit to the oldest key in the array if it needs it. It's my, yeah, you might want to add if it needs it. That's how it works. So I'm going to perform a sequence of insertion, insert 1, 2, 3, 4, dot, 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 n. So I'm inserting the 1, I start with an array of size 1, and this, you know, let's, it will be confusing with the dollars. So let's insert A, B, C, D, E, etc. These are my letters. So my array contains A, and A has at the moment $2. $2. It doesn't need to transfer this dollar right now because there is no older elements in this array. Now I'm inserting B, so I need to copy A from this part to this part. So now A have only $1. And B that just came has $2 as well. B is to, I think that the camera here is. So I have A and B that were just inserted, but how many dollars A have at the moment? A moment ago, when we started, A had $2. I just write a number without the dollar sign. You all understand. A right now has A at the first array had $2 left. A was copied into the new array after the expansion. It used one of these $2, so A has 1, and B has 2 at the moment. And you'll see I can make it actually 0 and 2. And now I'll double this array. So what will be the C, and A needs to be paid for the copy here. It is broke. B has 1, and before the next expansion, C is coming with 2, and D is coming with 2. What are they going? C and D are very rich. What are they going to do with all this? Fortune of $2 and $3? Notice that in the next time that I'm expanding, A is broke. A cannot pay for it being moved. A is broke. C is rich. C will give $1 to A. C will now have $1, and A will have $1. Yeah. Yeah. When C was inserted, it transferred one of its 2 if it needs to. Yeah. It needs to. It doesn't start so elegantly. It's more in the yeah.
So would this analysis still work if you kind of just discarded one of A's, like?
Yes, I could have dropped the fortune of A after the first part, and then B would, yes, that would be a better way to start it. The initialization is a bit odd. So A has $2, but as far as we know, maybe it has only 1. Because just for the beginning, you'll see the scheme when it works. I copied A, the first time that I copied A now have $0, but I inserted B with $2, and this was already a point that I could have transferred the fortunes, the funds, from B to A. B is the newer, A is the older. B gives $1 to A. A has 1, B has 1. Next, they are both copied to a new array. A now has temporarily 0. It used its 1 to be copied. B used its $1 to be copied. So they have 0, and that's fine for the time being. I'm inserting C. C is inserted with 2. has 2, D has 2. What are they doing with these funds? Transfer them to the older one. So we are moving to 1, 1, 1, 1.
Why only A with the $1, why not with $2?
A used its dollar to here to transfer it to B. Apologies. What the heck? Apologize. So unprofessional. Sorry.
The early size is 1. It has been associated $1 with it. First line,
When I started it was somehow an odd case. So I say A at this point, let's say, have to left $1 or was gambling on $1 and lost. So it has $0 it has $1 to be copied to here. It has $0, but B, when it was inserted, has $2. So B gave A $1 with dollars. So now they have 1 and 1. They are both, when they are copied, they are both using it to be copied from here to here. 1, 1 and 0, 0, 2 and 2. Transfer the funds. Now everybody has ones and so on. Cool. So all we need to make care of each insert operation is we need to put 2 new dollars. Okay. Now, what about contraction? So hopefully everybody understands that at the end, I spend $2. I never have an element that cannot copy for its. I never have an element that is being copied without having the fund to pay for the copies. When we'll talk about array, it will be used a lot in the hashing. Let's talk about the load factor. We have an array of size m. M is the size of the array. N is the number of keys in the array. The same notation as always. Usually for hash table, we don't want the table to be full. Hash are working very pathetically, very slow if the array is too full. We would like to keep this load factor after alpha less than half, practically. So essentially I'll say the moment that I inserted too many keys and alpha reached more than half, at this point I'll double. Now, back to our insertion so far. I'll still use alpha, but back to our insertion so far. When do I double the array? When I want to do an insert, but alpha equal 1. Agree? I'm doing an insert when I'm doing a doubling expansion when alpha is 1, the array is full, but I want to insert 1 new element. Back again into this key. And after this expansion, alpha equals half. Actually, since I did one more insert, it will be very slightly less than half. But when I'll double this array, it is because I wanted to insert E, so it will have 5 elements on M cells. Now, I'm short on memory. Of course, nowadays you need to give good excuses for why I'm short on memory, because it's a very fast cache, for example. Right? I mean, you have a lot of memory in your computer, but not all of it is equally accessible. The higher level of the hierarchy have much smaller memory, but are much faster. So now when I'm short on memory, then if I perform a deletion. For this scheme, let's say that I'm deleting in the same order from rightmost to leftmost. So I'm deleting D, deleting C, maybe deleting B, and maybe I'll decide that the array is too small. Or maybe I want to do it even sooner. So what should be my policy in terms of alpha? When should I shrink the array? One possible is when is the moment that I see that I can squeeze my array into an array of this size. The moment that I see that I used an array of size 2 to the I, I'm using an array of size 2 to the I. Let's say that the moment that I get it, so I can squeeze all the keys into an array of size 2 to the I minus 1, half its size, then I'll shrink it, copy everything into this array. Horrendous idea. Why? Because right now this smaller array is completely full. So the next insert takes me, I'll have to expand again, copying all the keys from here to here, very slow. Shrink, expand, bad idea. Better idea. We shrink only when the array is quarter full, 0.25. That's the homework. I'll ask you to play with different constants. So what was our invariant before? Let's get back to the case of so not too hard to think that now if I am in a position where every element has $1 and let's say has $1, I need more much larger arrays to make it work, but this $1 is paid for the deletion. Delete, it takes this $1, this guy still have $1. Let's keep shrinking, then now I need to copy the 1A into this area. Now it's A by itself, and now A is running out of funds. It was, every time that it's copied, it needs to pay for it. And the A, once again, or the 17 from the previous whiteboard, is being charged multiple times. It might be copied log n times. Right? I fill the array, including 17, and then I shrink the array. And but the same key, 17 or A, has been copied many times. Who is going to pay for these copyings that are caused by the deletion? The deletion operation. Every time that I'm deleting an element, I'm paying for another element that might be broken. Okay? And similar scheme will work if I change this number. I can decide when I delete and shrink, but it needs to be two constants. As long as these are two constants, then you are in business. And why is it important to think about other constants is that you are trading time. The smaller the gap is between when you shrink, when you double, the smaller this gap is more memory that you are wasting, more empty memory. But on the other hand, if this gap is very small, then you need to do copying very frequently. So it's trading memory against time. Think about it. If I'll shrink it the moment that if I'll decide that I allow the array to be 90% full, even in the sequence of operation, if I allow the table to be 90% full, then I'm spending much less memory. But when I double, I'm getting much less, only 10% more space until this is full, and then I need to copy everything again. So if I'm increasing it when it's 10%, so suddenly my sum will not be 2 times n, but will be 10 times n, if you're getting to 90% full. Okay, let's start speaking about splay trees. play a bit with this question. In the homework, let's talk about splay trees. Beautiful, beautiful data structure. So we all know what are binary search trees. 17, everything to the left of 17 is smaller or equal than 17. Anything in 17's Y tree is strictly larger than 17, and every search tree is arranged recursively the same way, left and right. And now when I'm searching for a key, I can insert it. When I'm inserting a key, let's take a concrete example, 17, 30, 80, and 99. And when I'm inserting 101, it's very simple. You're going all the way to the right, inserting the 101. That is, you're pretending that you're performing find of 101, except that you are running into a null empty pointer over here, so that's where 101 might be added, and we're all good. But then the question is about balancing. And balancing is a bit tedious. AVL is relatively simple. Two, 3 trees are fine if you want it to be only balancing with mean balance search tree. Its height is log n. So for balancing, I need to spend some memory to store a status for each key, like what is the height of its subtree, or how balanced it is. If it's AVL, is the difference between the height of the left subtree and the right subtree. And so I need to store all this information. And a splay tree, first it's unbelievable branding of a name, because splay is to make something in cooking, I think. People that have no English might correct me, but splaying is to take, when cooking, like a bunch of items, then push them down. And splay stands for self-balancing, self-adjustable. You know, I didn't write it. It's an acronym that defines the splay tree, self-adjustable, etc. Sorry about it. And it doesn't store any information. And it doesn't care about balancing. However, we will see that the amortized time for each operation is still log n. Even though I'm allowing the tree to be really not balanced, it will still, everything works. How many of you, showing hands, know about splay trees? One, okay, you don't. Great. New things. And splay tree are actually the basic idea that works about splay tree is let's perform just the find operation. Find operation, you know, look for the key x. And how should I arrange my tree if I say I have a sequence of find operation? Sequence of many find operation. %99 of the finds are find 99 or find 101. And only 0.0001% is find 17 or 17, 18, or the other one, or 30. So you see, 99% 99 and 101 are very common, and the other ones are barely performed ever. If I use AVL or skip list or red black tree, etc., all you're getting is log n time, and it's kind of okay, but will you do something better with this scenario? Some of the keys are extremely popular and some are extremely rare. Will you do something better? Remember, when I'm doing now find of 99, I need to go all the way down. So maybe balancing is not such a great way. You're going to access 100 so many times, 101 so many times, put actually 101 at the root and 99 the other one, put very close to the root. And the rest of the elements are somewhere there. But then I need to think a lot of time, how do I arrange a tree? Instead, what the spray tree will do, will say, every time that you're accessing a key, somehow push it, arrange the tree via rotation, push it to the root. Every time that you find a key, push it to the root by a sequence of rotation. The tree will not necessarily be balanced, but will be extremely efficient, especially if some keys are more popular than another, then it can definitely beat the n log n. Since you're research oriented, I'll tell you that actually it depends very much in the entropy of the whole system. If they are all equally accessible, then log n is the best you can do. So split tree are not worse than any other trees. But if some keys are popular and some are not, you can definitely beat the n log n time for these operations. To be continued. Thanks, everybody. Probably today, tomorrow, was. I mean, but, I don't know, like a week and a half. I don't. We need to decide about the midterm, so for the next meeting, try to see which other deadlines you have, so we can enumerate. It should be somewhere between, what is this, October 15 to November 5, somewhere in this environment. You have 3-4 weeks to pick from.